Okay, microphone is on right now. I made a terrible mistake for turning it off. I've been talking to the air all the time. Anyway, so here we're having the AS file. We're going to use 32, and then we're going to say, yeah, like that. But this is actually going to need, yeah, this is going to be a for each. So we're going to say for each file, in this case indies, we're going to do AS32, in this case file, that should be it. Let's see, is it compiled? -o file dot so. Yeah, this is crazy. CMake, you are freaking amazing. Okay, so build the HTTP and CTP files. Build the assembler files. Okay, so that's working pretty much perfectly. Okay, so we now also, we aren't linking the assembly files yet. In this case we have .s.o somewhere right here. So now we also want to add those files. So we have the .as file. So for each file, file.so. How about that? Compile arguments AS is okay, so this is completely working right now. As you can see, we have all the files. We have the make file. What we're now going to do is to continue creating our string. So in this case, we're going to, in the kernel HTTP file, not in the kernel, we're going to use test. We're going to say hashtag include lib slash lib slash ss slash string std slash strings.http. So now if I'm correct, you can just say std string right now. Std string str. In this case we're going to just create one like that. Alright, so is that working, or we're going to get a linking error? It's working. So in this case, our string right here, let's say uint, to also includes, in this case, types.http. We're going to say uint 32t as string len. Should by default be equal to 0, or actually 1, because if we want to get our length, or actually 0 to be honest. So we're having our string length right now. Okay, so oops, that's not good. Let's actually make these our own then, like this. So we have f instead of that. So now if you go to we're getting an error, so f. Great, cool. So now first of all, when we are creating a string, so let's say string right here, the default constructor, we are going to either have nothing, so it will set the current, it will allocate memory. So if it has nothing, we'll just say this as first byte will be equal to, oh that sucks. This really sucks, we don't have the heap of course. Oops, we don't have the heap. Yeah, this is not going to work like that. We're going to need to use buffers. We're just gonna... Okay. Okay, let's use namespace string. I'm going to need to use buffers. We don't have the heap. We don't have access to the heap. So we need to create a function called strlen. So extern uint32t. actually we're going to create whatever. Let's do auto reference strlenb for bytes, and then we're going to say is this. Okay. So by that we can create a string right now. So let's go right here. Grants full access to the system. Char buffer. Hello world. Should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we're going to say std strings. This is strlenb and buffer 0. uint 32t strlen. In this case, so we can calculate the length. So we're going to say sd south is the end line. Okay, namespace string. sd of Okay, so in this case we have the runtime bytes, which should be compiled, but okay. I'm not sure why it is. Okay, I think I see. We need to do this, and then we grab these right here. I don't know why this isn't working. Make clean. There you go. So okay, so there you go. Now it's working fine. We can now start calculating the string length. So first of all, when calculating the string length, we want to first of all store the original value of RDI, so the original pointer. So in this case, that's a math double word, I guess. Math double word. No, let's do it like this. So we're going to store EDI into R10D. So now we're going to say stores and copy of original pointer. Then we want to set math the \0 char to AL. AL will be the char which web needs Gatsby will search for, so in this case it will be AL. And then set the search char AL is lower register, so that's 8 bits, 1 byte. Then we're going to say web needs Gatsby, repeat not equals scan string byte. Okay, let's actually see if this even is called. So let's say math 0, ex, like this. It's working fine, okay. So web needs Gatsby. Then what we're going to do is subtract the new address, in this case EDI, and R10D. So we have the new address and subtract it from R10D, which will be stored in R10D. Subtract the old address from the new one. Actually need to reverse these two. Ooh, okay. Okay, now we can say dec decrease R10D, removes the zero, removes the null from the length, and now we're going to say math, in this case R10D into EAX, and that's not working. Not what you want. R10D from EDI, which some other way does not work as expected. In this case, EDI similar way doesn't contain a good value. Let's actually see what happens if we do it like this. Which actually kind of makes sense because it's not okay. Math EDI at10. We want to store the copy. We want to search for \0. Let's actually see this. Okay, there you go. We found the string length currently, so as you can see 11 characters, which makes completely sense. So now we're going to say returns the length. Cool, also take a look at this, it's working. So now we're going to say uint 32t constant char pointer a d for data. Calculate the string length at runtime. Perfectly, so this is working as expected. That /main.o /a.out, it's really fast. It's really fast. Okay, so that's really cool. We can now calculate string length. And what else we need to have is a string to integer. I mean integer to string. So extern c void f str int uint 32t to string, which will in this case have an int uint 32f num and char pointer red. Alright, so now we can say auto reference. I don't know what a toy means, but it's by default used in C++, so I think the name makes sense, I guess, so let's just use that. We're using these, by the way, because we're using extern C in this case, the C calling convention, C calling names or something. It will work like this in assembly file, so we won't get randomly generated numbers, so that's why I tried to create a really long string so we can never override it with another thing or something accidentally. So in this case, a toy. What we want to do is actually loop over the number. In this case, let's search Google on how it works. How does a toy work? So actually, I'm going to grab something that someone else made for this. I'm not going to create it on my own. This already someone has here. This is it has a function somewhere right here, which basically does that. itoa insert to a. Let's see how it works. Count. I think I see. Yeah, this makes sense. So what we first of all want to do is get the string length. So we're going to say that the global. You know what? We can just do it like this. So first of all, count the amount of digits. This is going to be a large assembly function. Okay, so void let's see what's smart here. It's strings HP char pointer red. So what we first of all want to do is start counting digits. So we want to create a copy of num. So in this case, moth edi into in this case ECX. In this case ECX is EDI, ESI, EDX, ECX, EBX is not one of them. So stores copy. Copies value EDI, I'm going to say prepares for looping, So now what to do is create a loop. So in this case we're also going to have a count in this case, which will be used with XOR, and then we're going to say EDX will be the one that we're going to use. EDX, so in this case sets EDX count to 0. Now we're going to say loop right here. Count loop. I know these labels are freaking long, but I don't care, to be honest. And now we can say we want to divide our number by 10. Div. In this case we want to divide ECX by 10. AT&T syntax need to do that like this, I think. Let's see. Ooh, that's not good. Div D. Actually, divide can also be used with shift left, I think. Google, how to use div in assembly. Okay, AX will in this case hold the dividend. Let's actually grab my assembly book to see where register AX is and if we already use that register, because we don't want to. AX is for, I think, from EAX. Let's check this out. AX is from EAX, not in use, so we don't give a F about it. So now we're going to say math. In this case we want to move 10 inside of EAX. Ah, cool. Okay, so 8-bit division using div requires AX for the dividend and an operator. EAX, I think, right? Yeah. Okay, so now we divide successfully. Let's see, yes, still performance. I think you see if segmentation fault is occurring. So if we go to strings, in this case, we went to what function are we creating? Yeah, integer to blah blah blah. If we're going to main, we're going to say uint 32f. A will be equal to 105. Alright, and now we're going to say char buffer. Buffer which will be 12. Will be backslash 0. Then we're going to say std str uint to string. Then we're going to give a and the memory reference to buffer 0. Just like that. Okay, so std south buffer std. We're not modifying the buffer, I think, so. Ooh, that's not good. Let's make a separate scope for this one so we don't have to deal with that crap. Okay. Now we're receiving something completely empty. You know what? We can just move it like that. Happy like that. Alright, so currently we're doing not anything. Let's go to the file. So we're just dividing. So in this case we can actually check the amount of digits we have. Let's actually do that. No, we're not going to do that. Okay, so we're having division right here now. I actually need to do this, I'm afraid. ECX. Okay, so let's say sets the divide value forms the division. So now we're going to check while number is not equal to 0. In this case with num, I think we're talking about ECX, so performs the operation, checks if it needs to loop again. So now we're going to say CMP, in this case EAX against 0. Actually, we can just do test EAX against EAX. We don't need to set a bunch of flags. ECX, I mean ECX. Let's see if this gives an error. Nope. Now after testing, so sets the flags 0 flag in this case. Now we can just say G and Z, jump not to 0, and then we can just say jump again if it's not 0. Alright? Okay, that's not good. It's going infinite. What if we do CMP? Floating point exception, what? Oh, IDIV, integer division. Yeah. I don't understand. Assembly divide int by 10. Okay, assembly divide int. I know you have to use IDIV. Oh, jump 0 if not 0. What? I don't understand actually why this is happening. We're getting a floating point exception. Can we just do AX then? It's not dividing, isn't it?
question. So if you're flip, is that confusing? What the word is? It's horrible.
I see.
And where does the quotient go? The answer. Where does the remainder go? Alrighty, let's have a look. So, first of all, the divisor that we give, and the implied dividend. And where does the quotient go? Word, the quotient is going to go into AX as the implied dividend, and the quotient goes into the AX, whilst the remainder goes into EDX. And then dividend, and where does the quotient go? Cancel. Where does, and we're going to get back, okay, so if we've got, we want to do, say, x over y, x divided by y, we give it y, and the x is implied. That's the divisor. And we're going to get back the quotient, but we're also going to get back the remainder. Alrighty, let's have a look. So, first of all, the divisor that we give, and the implied dividend, and where does the quotient go? The answer, where does the remainder go? I never remember that. But anyway, if the divisor is 8 bits long, if it's a byte, then we issue the command idiv ECX. What's going to happen? Be trouble. Most probably, because what dx? This is where the problems start. This is where using these instructions becomes very dangerous. EDX could have anything. So say EAX has 10, that's cool. It's a 10 over there. But EDX, EAX might have F, F, 2, 1, 4, 8, 7, 8, and we divide that number by 5, we get something stupid that we don't care.
Okay, so we need to reset EDX, I think. I just realized, because it will contain the high bits. In this case, because we want to actually check if it is even working, so we need to some another way. Now we need to change this to uint32f, I'm afraid. I don't care about that. Here you go, because it's counting, I want to actually check how many digits it has. So let's actually see what our thing has stored for us. So if you now go to our test.cpp file and do std south, you might actually see some 1 digit. That's not correct. Okay, so we made a mistake somewhere. Was expected. Was definitely expected. While we reset R10D, removed. Maybe we need to do this. Well, just one SV. I see. Yeah, I don't like this. The quotient is stored in EDX. This, you know what this means? That we need to store EDX every time. I'm not. No, why? I don't. Wait. Okay. So we're going to remove all of these except increments. Okay, so now it will loop infinite. In this case, ECX will be used to store the leftover numbers, but first of all, let's actually see if ECX contains what we want. Let's remove this for a second. 115, indeed, it works. And now I'm wondering, so if you do XOR EDX and EDX, and then say mov, in this case 10 into EAX, which basically, okay, and now we do IDIF ECX. What will it do to ECX? Absolutely nothing. But if we check, in this case the quotient is stored in EAX, we can say, we can remove this line, I guess, or not. Let's see. Divide by 10. And how about divided by 2? Okay, if you divide by 10, maybe you need to have to remain it then or something. EDX then. Divide by 4, 5. Actually, first of all, make sure that our division is actually working. In this case, ECX contains 115. Was I performing a division? What if I just do diff? So wait, we're using, let's do 11D then. How about then? Still stores 5. Divide by 2. Let's divide integers. you know what we're going to do? We're going to go to our main.cp file and we're just going to say 20. Will we get 10? 12? Why do we... This is awful. This is crazy, man. Okay, so we're storing EAX. We're moving data into EDX. Because we're doing an ED word, that's 2. What? Man, what is this thing doing? Integer divide. Should I get 12? Why do we get 12? I don't understand. Into EDX. Oh. Oh, wait, no. We're dividing. Quotient is stored in EAX. But when we get a random number.
Multiply, divide, and remainder. And so the flip going to write down back the yeah, it should be. Here we go, here we go. Let's tackle divide. What are we going to do here? We've got to return A.
And put it into EAX. So in this case we want to divide value of R10D and we want to move that into EAX. Don't ask me why I'm following this tutorial.
I just said we need EDX to be nothing, but in fact we need it to be the sign, not EAX. Alrighty, so we can't do 0 EDX, that's going to lead us to trouble. Anyway, this is so here's the X, this is move the dividend into EAX, so maybe it was an ECX, since EDX, EAX is implied dividend size. So now the other thing that we need to do.
Dividend. Okay, RAD EDX.
set EDX to be the sign in the AX. If the dividend happens to be negative and is 0, EDX, just like that, then the implied dividend, the 64-bit implied dividend, won't be negative, since the leftmost bit of EDX would be a 0. So what we've got to do is copy the sign bit of EAX all the way through EDX. It's going to be all 1s, EAX was negative, and it's going to be all 0s, EAX was positive. Now there's a couple of ways you could do this. We went through one way with a bunch of arithmetic shifts, but this is actually so common an activity that there's a command to do it. So CDQ is 1, sign, extended. Say copies actually fills with.
Ladies and gentlemen,
It works.
ha! Okay, EDX is not used. We can now actually put these at the top, I think. So EDX will be resetted, and we will put the divisor. Right, that's the divisor. I don't know. We want to divide by 10. Now we get 2. Okay, so sets the amount we want to divide. Resets the EDX register divide. So divide is actually working properly. Now what we want to do is store the results of idiff, which is in this case stored inside of EAX. Wait a minute, what if we just do this? Wouldn't that be more smart? Not just the same thing? Yeah. Huh. Okay, so now if we just say checks if it needs to continue. First of all, we're going to increment, so inc, in this case the count, which is R10D, increments the count, increments the count, and then what we now want to do is test, in this case the EAX register, and G and Z we want to jump back here. Basically now we should get 0. Yeah, okay. And now what we want to do once it's finished, we want to say move, and then in this case R10D into EAX. Now we will probably see 2 digits, okay. And if we go to the CP file now at 202, we get 3. Oops, that's not good. 205. Getting a floating point exception. Okay, what if we do 20, 200. We get 3 digits. But I do not know why we're getting a floating point exception. No, we get, yeah. Probably because of this, I think. We need to do this every time, doesn't it? Yeah. Except for this one, of course, but we need to clear the register each time. Yeah, that's working. So now if we add another 2, we get 4. Ha ha ha! Cool. Okay, so now we are successfully getting the amount. So first, so performs the division. Performs the division. In this case, that is EDX is EAX. EAX, EAX. Okay, so now we can say sets the bits, sets the flags 0 flag what for most, and then jumps, jump if not 0. Okay, so it is working. Now we're going to say moves the digit count into EX. So now what we can do is start turning them into string. I'm already pretty happy with this actually. We can now actually check the digit count. Let's see how far we can go if I add some random numbers here. Now it will be 6, right? Cool. So we successfully count the digits. Well, now we know how the division function is working. We can go back and we can actually, I'm not going to write this in C++. I'm going to write this in assembly. So you can now successfully count the digits in this case, as far as I see. So we have the digits count. We count the digits successfully. And now we have an index, as far as I'm seeing. So in this case, the digit count is already stored in EAX. So what we can do is now start. Where's the file? We can XOR. So prepares XOR R11D, R11D, and we XOR it to R11D. R11D sets the index. Index will be 0 in this case. Let's see how this guy is doing this. I mean, the person who did all of this is actually pretty smart. But we have the digit count in this case stored in EAX. Number of digits is EX. R10D, we can actually reset. Reset the index counter. Okay, so R10D, R10D, alright. Just resetting the counter, but it still receives 6, of course, because that's what we want. Now we have, because we moved EDI into, so let's say full number is EDI. Now because we didn't modify EDI before, we can just continue using that number. So we're going to reuse this function again with digit count. We're going to create a loop, but we're going to loop over the count we already have. So starts looping. So here we're going to say count loop, build loop. Build loop. In this case, performs the operation. And then checks if it needs to continue. In this case, the index will actually be set to EX, but that's not required. Yeah, ha ha ha, we already know it. EAX, okay, we have EAX and I want to decrement EAX. So dec EAX, and now finishes mov, in this case R10D into EAX, because we still want to see the length. So restores the digit counts. Bloop. Yeah, there you go. So we decrement EX. If you didn't do this, we would actually see 5 right there. No, maybe not. No, that's of course because it's that stupid thing. Yeah, 5. There you go. Okay, so we're going to compare. In this case, so what I'm seeing right there is one number is not equal to 0. So CMP, in this case EAX against 0. J and Z is what we're going to say. G and Z works. Yeah, fine. So let's actually see if we can actually put some charts in there. So we're going to say math stars B doesn't see what it does. Is it most likely mess? Yeah, it messes things up. Cool. Okay. So we know that it's looping correctly. So what you now want to do is, as far as I'm seeing, we need to use mod. Okay. Number mods then, so that we need to use division. Okay. I'm going to go to the toilet and I will be back. We need to use modulus. Modulo is simple. The rest, what's left? In this case, if we do idiff and then get the quotient or something, what it's called. Let's actually see. The remainder, we need to get the remainder. So what we're first of all going to do, in this call XOR EDX. Ooh, that's going to be an issue. Because we're using EAX for that one. Well, we're dividing, but if we do push EAX and then pop it after that, pop EAX, operand mismatch, pop D, okay, we need to sort in temporary register, so we're going to say move value of EAX into R11D, and then we're going to say move R11D into EAX. How about this? Still getting 6. Good. But now we have divided. In this case, the quotient gets stored in RDX. EDX. Oh, I see. So in this case, we want to use EDX. We're resetting it right there. And if I see the script right here, we're storing, in this case, EDX, which will be the remainder, and the remainder will be added to the current memory register. So in this case, we're going to say add, in this case, the character 0 to EDX. Okay, that's working. And then we're going to say mov the value of EDX into RDI. Okay, nope. The first one of RSI. Okay, let's actually check out the stosb instruction. Stosb. I'm not sure where it's being read from. Store a EDI. Yeah, that's not what we want. We don't want to use stosb then. So we need to create keep an own index register. In this case, R11D is already in use, so we're going to use R12. XOR R12D R12D sets the counts to 0 for memory, and now we can also increment, in this case, the count. So we're going to say R12D, and now if we put R12D right here, that's not good. Okay, so I think what we're going to do, so here we have RSI, and we want to put in the memory location right here. We will get 0, of course. But now if we say, we're currently having this, and now we actually don't need a count. I think we can just do add RSI, we should basically go forward one in memory. ESI, of course. That's ESI. Ink, actually. Oh, okay, that's not good. It's giving a segmentation fault, which means that we're writing to memory that isn't ours. That's not good at all. In this case, ESI, ours EDI ESI. In this case, red, which actually should work. We should have. What if we do this? We increment the. No. We want to move it into ESI, but why isn't it working? If we do this, RSI, alright? This is most likely because we're not using 32 bits. Yes, okay. Found the issue. When we're working with pointers, apparently we want to actually say 32 bits, so we're going to go to a make file and we're going to actually enable the 32 bit ones. Let's see. Oh. Okay, so we're not allowed to use these registers. That's stupid. Well, you know what? Let's do some refactoring then. I'm grabbing my programming book. Those are not much. We have RBX, we have RSP. Ah, crap, this is not good. Ah, fuck. This is going to be hard assembly code. We're going to need to. Okay, so in this case, we're not using RSP. We are using RSP. RBP is not used, so we could. Ah, damn it. Isn't it possible to just compile 64-bit? I think I'm going to make my wall sing 64-bit. Segmentation files coordinates. Okay. Well, because this is unfortunately the case, we are going to need to use 64-bit stuff, and I'm not sure if QEMU will like that, but I don't care that much, to be honest. EDX. Okay, so when we're dividing EDX, let's see the tutorial again, will hold the remainder, and we're currently dividing EAX. Let's actually see, we're using IDIV RAD while R8D in this case. Okay, so we're dividing EAX while we actually now want to do RAD, which actually still contains the old value. Oh wait, what? Is it actually? Nah, it's not working. 500. Let's see. I was wait, like, what is it? It can't be working. If it would work, I'm going to literally laugh really hard, but it's not working, so that's fine. Now is my question though. Why isn't it working? So let's go back. I don't care about that here. What is that mother effer doing that I'm not? It's the mod, it's working, that's mod should be working, but now I'm realizing it's where is the stuff start? In this case EAX, where's EAX, MOV EAX R11D? Now I actually just forgot. Okay, what is EAX? Okay, so I think I see the issue with dividing. So stores and copy. Stores the count. Restores the count. Restores the count. But in this case we're not interested in that. We want to move, in this case, the value of EDI into EAX. Or not. 20, if I do 20, will it work? 202. It's somewhere doing something, but it's not the way I want it to. So I think I'm going to remove this code right here. So first of all, we want to, in this case, EAX stores the count. I'm pretty much aware of that. But EAX, why don't we? Yeah, okay, that makes sense. R11D, right? The length is working. R10D right here. Okay, so we're going to first of all MOV EAX into R11D. MOV, in this case, R11D. Can actually just do push. So push. No, that's not fast. We're not going to store it in memory. So we have R11D right here, and now we're going to say MOV R11D back into EAX. So first of all, stores the original value of EAX, restores the original EAX value. But now what we want to do, so in this case, when we're looking at this, we're currently going to need to write the original number. Not the original number, to be honest. We want to store, in this case, the number that we have used in the previous one. But in this case, you can see EAX is the counter, right? Now we want to actually divide. So let's say MOV, in this case, we want to move EDI into EDX, into EAX. So EAX, so sets the number to be divided. So now we actually store the number that we want to divide. But now it's also really important, because EAX will, in this case EDX, will hold the result of our dividend. Let's actually see what it's doing right there. So yeah. Okay, so first of all we're going to divide itself for the value. But then we want to store the, I think I'm getting it. Okay, so what we're now going to do is, in this case, MOV. In this case, we're going to store the value of EAX, which in this case will be the result. So in this case, the quotient, not the remainder. We will move that back into EDI. So stores the division result into EDI. In this case, this will allow us to modify the value next time. But now, if we do IDIV, let's do this IDIV. All right. So IDIV, in this case, RAD, because that holds the value we want to divide. It will actually divide it for us. But now, because we want to set the char, if you are understanding me, we want to actually add, in this case, because EDI or EDX actually in this case. Let's check the YouTube video. EDX contains the new char one. So first of all, we want to add the 0 char to EDX. So first of all, okay, performs the division. And then we want to say add num of char 0 to res. And now what we want to say is MOV, in this case the current char. so in this case EDX, into the memory address of RSI. Ha! Floating point exception, we would have expected that. It's funny. Okay, I'm not sure where this is coming from. Okay, so we need XOR, EDX, XOR. Let's see if it's working. Yes! We did it! Ladies and gentlemen. Okay, let's add a large number. So we have 10,024. We get 10,024?
We did it, but in reverse.
We did it, but in reverse. Okay, so in this case, I think this is because, first of all, okay, so you can see right here RSI, right? We actually want to decrease RSI, but we want to add, in this case, the values of RSI. So actually, okay, let's do this. Decreases the index from the count, decreases the memory pointer, decreases the pointer to the char. Now checks if we need to break. So actually right here we're using compare. I think we can also do test. In this case we can just enter EX right here, which will most likely, so it's not 0, it is, let's see. Oh no. Okay, that might not be the... Oh wait, yeah, of course, if you do right here. As you can see, it's working, not perfectly, but now what we want to do. So here's we're going to say starts the loop, or not actually, we're going to say add. In this case, we want to add the amount that's in EAX. We want to add the value of EAX to RSI. So now, oh, that's not good. To the point of ESI. So we have EAX, add SXD. Okay, so we need to do mov SX day. SX. We want to day. In this case, we want to do the value of EAX and move it into RBX or something, R10 or R11. Are we using R11 right here? Okay, not that much. Now if we do R11, actually see. Okay. Ha. I think I'm a complete idiot. Take a look at this. If we now increment it, it works fine, but in reverse. This means that you see if this guy doing it in reverse. I think yes. This guy has the original EAX. In this case, EAX contains the count, and he is not incrementing it, but he's decrementing, decreasing. He's not actually doing it like that. He's. I see. Ladies and gentlemen, I did it. Haha. How about this? Nope. Okay, that's very much disappointing. What if we do this? And then we have the one. No, no, kidding me? Oh, yeah, of course. Okay. What if we just do this? EX. Want to add this one to it? No? Okay, well, at least we're storing 1. Inside of there. I am not sure why it's 1. We're decreasing EAX. Which means we're going from right to left. Let's see how this guy is doing that. So the index is decreased, right? Which means that we also need to decrease our index, but I'm not sure. Which this actually kind of means that we need to increment RSI. Let's see. RSI. But then we get nothing because it's null. And what if we now do dec? Decrease RSI. So we're decreasing RSI. Alright. We should get add, let's say, 4 to RSI, which is now it's the strange part. So it's actually displaying 1 right now, but if we do add 2, do nothing. 5. So some are not away. It's not properly working with memory right now. I'm not sure if we used RSI somewhere else right here. We're decreasing RSI. Yes, I know we're decreasing the memory address of RSI, but we actually want to start working on reverse on it, but that would mean that we need to go. Now that's the CPP file. Actually say we want to give the buffer index to 4. Right, and then just go back. But that's not doing it either. That's the thing I find really strange. 3, I like this. It's storing 1, so I'm not really sure I'm going to deal with this. Let's actually continue working on this. So we're already doing it quite well. If we now increment RSI, it works sorta, but not in the way we want it. It's just now the exact reverse, exactly opposite. So I can show you that. If we now make 8 of this, I'm pretty much sure it will be 1, yeah, 8201. So I'm not sure where else we are using RSI. Nothing up here. Well, let's actually say moves the char into the memory address. So it's working, but not the way we want. And I'm really not sure why this is happening like that. I mean, we have 4 chars. If we decrease our index, so you could of course say in this case we have RSI as our index, but now I'm actually thinking of it. Why aren't we using 64-bit integers for this? Because it's not required, of course. But what if you just say add, in this case, we're going to add EAX to ESI. It's a segmentation fault. Can you believe it, man? Oh. We're not supposed to write in this memory or something. So I want to add 4 to our position in memory, right? Which results in an issue because we're not using the pointer properly. But if we do 3, how about 3? We'll now store everything. We'll just store 1. So that's the complete crazy part about this. It's some other way not storing it properly. So and I have multiple theories about it. It has something to do with count, maybe it has something to do with count. But let's actually see what happens. So we know it's my phone. I need to find out how we can do this in reverse, how we can put the char in reverse to our register, but maybe we need to add 6, I really don't know. I really don't know. RAX, how about if you do a rex? In this case, rex as the... Yeah, God. What if you do L1? Okay, so now we can actually see. Let's add stripes for the characters, which are not set by us. So if we currently remove this, will it display all of those chars? No. I think I know what the issue is. Okay, so here's the buffer. For char I is equal to 0, I is lower than size of buffer I plus plus. Now we can just say buffer red I will be equal to a dash. So just can check out which. Nah, that can't be true, right? Is it messing up? I think I found the issue, but I'm pretty sure I didn't. So we're adding a number right now, okay? Now it's nothing, that's because we're decreasing it, but if you do inc, you get a to 1, but why? Is there... Wait a minute, we have 4. If you check our count, it says 4. Something is working in my head, but it's not working properly. Let's actually see set buffer 4 to I think I might have the issue, but not sure. So if you have buffer 4, it's the strange thing is, so some other way it's managed to zero out all of the other ones, which is not what I want to happen. So if we go 5, it's looping, but it doesn't stop. If you know what I mean. So that's just for the test. Okay, right here we're jumping if not 0. I want to test, want to check. Checks we need to break. So what if we do this? Yeah, okay. G and Z, but again, the strange part is that it's some other way it manages to reset it, and I think that the issue is laying somewhere because of that. So I think EAX, okay, we're having EAX right here. I'm going to create a new counter, so XOR R12D R12D. I'm not sure if I'm allowed to use this, but I don't care actually now. Just want to check out how many times it's actually looping, because that may be an issue. So if we get R12D right there, okay, we want to move the value of R12D into there. XOR, no, of course not to make a register. It's looping 4 times. 1, 2, 3, 4. Which again, wait a minute. Let's remove all of these. Okay, so if we add decrease at the top right here. Oh wait, no. If we add decrease RSI right here, or increase RSI, that's not working obviously. It's doing something. Want to decrease RSI. Now it doesn't do anything, but if we now say we want to give the memory address to RSI4, get what the frick is going on? Let's actually see what is $L. Okay. Jeez. Okay, mod B. With LLL, why there? And is idiv using RSI? No. How about this now? It's adding them inside of there, okay? Which will mean if we do decrease RSI right now and say add $4 to RSI. This is giving me hope. EDX. Which I'm not supposed to have. Mov byte dx, how about this then? DL, we're actually, I don't know why we're using longer registers for this. Ha! Ha ha ha! Add byte. DL. There you go. EDX. Okay, so that's working. We're currently successfully transferring our... Oh yeah!
Yes, bitches, it's working!
Okay, so now I'm seeing DL, that's EDI in this EDX, right? EDX, yeah. When we're dividing right here, then we're adding it to DL. DL is in this case returned by EDX. Yeah, this is exactly what we want. This is exactly. Oh my god. Okay. Well, now in order to increment it, we're going to say mov sx for sign extents and is that sign extent? Yeah. Mov lx, is that well? Mov x sign extent, yeah. Now we're going to sign extend EAX into register R11. Now we can just add register R11 to this one. So this process will be automatic. Now if we do this, we get our string. Okay. So now we say sign extends EAX to 64-bit rec. Now I can say add EAX to total buffer. Okay, so this is completely working. Cool. So as you can see, we now created a function which in this case converts integers to strings. So I'm going to test it out actually. So if we do now blah 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 right here, will it work? Yes, it does. Now if I do 9292457192647164117, 6417, it's working perfectly. 22, yep, also 66. Okay, now we got an issue. But that doesn't matter, we get it's okay, it's an overflow. It's overflowing, okay. So but now it does its job. As you can see, we can now convert an integer to a string. which will be really helpful later on. So now, I don't know how much time I spent on this, but it's definitely worth it. Take a look at this code. It's Georgia. It's beautiful. This code right here, ladies and gentlemen, turns an integer to a string. Now I'm actually realizing that we don't need to use it like that. We can just say blah. Okay, I think that works too. Fine. Let's say, for example, we have 1024. We get 1024. Now there's one thing. Ha! Scheidsschobbel. Een nieuw systeem, pa. Okay, either way, so now we're going to say decreases the pointer. Decreases the pointer. Now what we actually can do, because it's decreasing the pointer immediately, we can now say math, in this case char \0, directly into RSI, because we're decreasing it anyway. So, oops, that's not. Let's remove a byte. Char 0. That's the null term. So that's the null term. But I'm actually kind of curious. Now it's looping 4 times, right? We started 4. Yeah, that's working fine. Take a look at this. Yeah. It's converting a string to an integer. I mean an integer to a string. Okay, so now that's working. What else we want to do is currently start creating our... Start reading from our CMOS. Or what we're going to do. I'm kind of curious if this works on... But let's start reading from a CMOS. So in our HTTP file, we're going to first of all add if and def std CMOS header hashtag define std CMOS header and div. Now we're going to create a namespace std namespace RTCMOS. This is RTC. And now let's say, let's first of all create a uint 8t 8f. So we want to include our types header, include types.http. So now we have that done. We can say uint 8f get okay. RTC get weekday, for example, right? So this will basically return nothing at the moment. So we're going to also define our... we need to create a macro for that one inside of the assembly file. Let's actually get some node spray and let's create our assembly file then. To do the same make, we can just simply create our assembly file right here. So CMOS. So we can just say CMOS rtc.s. As you can see, it will automatically be compiled. Is it automatically being compiled? No. Okay. Well. CMOS rtc.s. Extern f CMOS rtc get weekday. In this case, return a uint 8f. So if now go this dot global blah 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 and this is blah blah. I don't know why it's... Why it's not working, I completely don't know. What if I rename it to RT? Will it work? Yeah, okay, so I think I see the issue. We cannot shit. Google make file for loop. Ah crap, this is a lot. For bigger ranges, number one while blah 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 do done. Okay, so we're compiling assembly files somewhere. Here. What if you just do this? Ah, crap. This is annoying. Why does it have to be like this? Okay, yeah, whatever. I need to do this differently, so currently we're doing it like this, and now just whereas it's okay. How about we do this? Object assembly files. How about this then? Okay, that seems legit. For file in do done expect. Okay, so you have an S for that. S4 file in do Why did people make it like this? It's stupid. Okay, for file in do done. Now, does it... I don't know, man. Why? Why are you doing this to me? This is not fun. I don't know. For file in syntax error done unexpected. Well, I don't care. Does it look like I care? Yeah, I care about it. Whatever. Okay. Okay. Echo. AS. Well. Nope. It didn't. Nope. Ah, frick. Well, this definitely sucks. Now, does it print it? Apparently, it can print it. Yeah. So that's better than nothing. AS. Well, can we do file? Apparently not. Okay, so now we can grab our file or something. Let's see. Now we can say and apparently it can. What if we do an echo? Okay, so now it works. Okay, well, cool. So now we can start using our CMOS file, I guess. So right here now CMOS HP file, we're having this function. Well, what everyone needs to keep in mind in this case, that you auto reference, and then we're going to create a reference to this. What we need to keep in mind is in this case that the CMOS is currently not allowed by Linux to be used, so we need to actually override it. That's why we have these permissions set right there. But now if we open our CMOS file right here and we check this function, so let's actually see how we can create macro. So let's check this out. Global macro inside AT&T. GNU assembler macro. Otherwise you're going to have to do a data section. Yeah, I don't care actually about this. Well, as long as the CMOS chip doesn't change, I think we're fine. Okay, so this will basically fetch our data. Okay. In order to do that, we're first going to use out. In this case, the out will write the address once. In this case, when we're wanting the weekday, we're checking at 0x06 or 0x6. So we're going to say muff. Let's actually check if our tab space is the same as in the strings file. I want to keep consistency. So if you do this and then go to the... Oops, that's not... Okay. So let's copy one of these lines and paste them right there so we can actually see how we should format our file. Which is actually pretty important. So in this case, my tab space actually was correct. So now we're going to say $0x06 and we'll move that into AL, I guess. Let's see if this is giving any compile errors to us. Not. That's cool. So now what we can do is out, and then we're going to say we want to write AL to register 0x70. Alright, so this is going to give a segmentation fault, most likely. Not. Unfortunately, we need to include it. /lib/cmos /r cmos std cmos rtc. So now if you say rtc std cmos rtc, this is get weekday, and now we say std south right there. we'll get an error. Segmentation fault, to be honest. Ooh, wait a minute. Undefined reference? How is that possible? Ah, I see. It's being smart. Now we get a segmentation fault. Yes, we get a segmentation fault. Okay, so in order to fix it, just have to add sudo in this case. Now, as you can see, it works! We wrote! Okay, so as specified in this documentation right here, the CMOS has in this case a small register called A. Let's check it out where that's standing. So, register. Let's see. Okay, in this case, that is register A, and if we want to access it, so RTC. When chip updates, time increases seconds, roll over. Bit 7 of the status register A. So in this case, if we want to check if we can write, so we're going to create a new function called the global fcmos RTC wait for update. In this case, it will be stored in the register 0x0A. So we're going to wait for update. So in this case, when we call this function, we'll create a loop. So what it will basically do, we're going to compare, or actually we're going to say in, and then we're going to store, in this case, the value of AL, or 0x, let's actually do 0x71. So first of all, going to write to the register, so we're going to say mov, in this case, 0x0A into AL. Then we're going to say out, and then we're going to write AL to 0x0A, and after this we can actually check. So we want to check the 7th bit. In this case we can do a bit test, I think. Not a, let's see. Google assembly test if bit is set. So I think there's a bit test for that. But okay, that's the carry flag. So when we perform a bit test, the carry flag will be set. Alright? BTS, the BT is instruction bit test, copies to the carry flag. So the carry flags can be received. Okay, so now in order to perform a bit test, we want to check the 7th bit inside of the register AL. So now we're going to say BT. We're going to give AL, and we're going to say position 7, I guess. Ooh, there's an error. We want to test for position 7, and the carry flag will be set accordingly. BTB bit test byte. Okay, so I think the bit test in this case need to register like EAX. In this case AL, let's see where AL belongs to. AL belongs to register EAX. So we're going to say EX. Check. In this case, because we're using EX, we actually want to XOR EX in this case. So XOR EX, EX. I'm going to say sets EX to 0. So we actually want to create a loop now. So because we want to wait, we're going to create a loop. And now inside of the loop, okay, so perform requests the status register A, checks status register A at bit position 7, 4, and 1. Okay, so if I'm correct, let's check this out. RTC update in progress. When the chip updates the time and date once per second, it increases seconds and checks if it is roll over. If seconds did roll over, it increases the minutes and checks. To help guard against this problem, RTC updates to read the time and date properly. You have to wait until update flow goes from set to clear. So if it goes to clear, it goes to 0, I guess. So in this case, we want to check if the carry flag is a 0 at the moment. So in this case, assembly check carry flag is not set. So in this case, we can say GNC jump if not set, and then we're going to jump right here. So in this case, it's going to wait until the corresponding flag set. It's going to say call, and otherwise it's going to return. Okay, that's not okay. It's actually I think we have to wait for it to return. So while writing out this, to say no op a few times, no operation, no operation. Okay, can we say AX? Okay, so this should do it. So I think I made a mistake because we didn't do the correct thing. Okay, so in this case, when we're checking right here, RTC update in progress. When the chip updates the time and date once per second, it increases. To help guard against update in progress, to read the time and date properly, you have to wait until the update in progress that goes from set to clear. So in this case, from set to clear means that if it is still in mode set, so in this case mode 1, you want to go back to the top and just wait a few times. So going to add a few no operations right here. No operation skips 2 clock cycles. Okay. As you can see, we can now properly wait for operation to occur. So let's add some comments right here. So skips a few clock cycles. Okay, so now moves 0x0a over the to address, moves sets that we want to receive the status srec a, sends the value which we sends the register value over the bus, receives the value from the bus. So in this case, I think we also want to add a few no ops right here, no operations. Actually, I don't want to have any no operations. This is working properly, so now we can actually request. So it checks if bit 7, if update in progress, jump if update in progress. So now we can successfully wait. Alright, we have the loop set, and now we can just wait. So first of all, we're going to say wait until register is safe to read. Then we're going to say does it save, and then we're going to say request the weekday. So when we request a weekday, we're just going to write in this case 0x06 to the over the bus to the CMOS. In this case, the CMOS RTC part. Okay, and then we want to receive it. So now we're going to say in, and we want to receive in this case the value from 0x71 into AL. See, which currently works, funny enough. So it's now reading data properly, but in this case AL, let's see where it's from. It's from EAX actually, which actually would be nice to actually clear. So XOR EAX, so that EAX is ready for proper use. And now if we go to our test.cpp file, we actually see out that uint8f is what we're returning, so we actually should see some results now, but it's not returning anything, isn't it? AL is 8 bytes, and that's exactly what we want actually, an unsigned char. But strange enough, it's not receiving any data. Let's actually add a few no operations right here. What if we add 0x00? Okay. Okay, so the seconds are working. And I'm sure because we just need to cast them to an integer now. I think that was the issue, because they're too low to be seen as integers. In this case, you have 64, 65, 66, 67, 68, 69. Why? Okay, the seconds register is not working properly. Something. But if we now do 06 for the weekday, we will receive proper one, right? We receive 1. If we do 07 for the month day, it will be 4. Is that correct? It's the 4th one. So actually to check if what we're doing is actually waiting for a proper read, we're going to this is going to be fun. So now to check for a proper read, we're going to do this. Creating a loop. And okay, so as you can see, all of these values are constantly correct, and this means that it's reading properly from the CMOS. Wow. Yeah, it's reading properly from the CMOS now. Cool! Who can tell their friends that they read data from the CMOS? Haha, this is so freaking amazing. Check this, I can literally... Okay, it's 7, 8, 9, 16, ooh, 19. Okay, the weekday is working, let's see, it's the first day of the week. Cool. So, it's working, so we're going to say clears the bits of the EX register. And now we're going to say moves 0x06 to AL for the weekday. And now we can say write 0x06 to the bus. To the bus. Reads from the RTC return. Read from the bus. Alright, so it's working! Can you imagine that? It's freaking working. So we get a weekday. Now I'm actually kind of curious, in this case a century, 32. Is my computer smart? We're in the... No, it's my computer is not smart. The month, which month is it? It's what? Which month? I don't actually know. It's May, January, February, March, April, May. It's 5th or something. 5th. Yes, it's the month. Check this. Check this. Check this. So actually, in order to fix this, I don't like it. I don't like the way of we're doing it right now. So we're going to refactor this. fcmos get value. So in this case, fcmos get value will have a value. We will give an enumerator inside of it, and the enumerator will be stored in this case in the value of RDI. RDI. Actually, we don't need. It's not a memory address or something. It's just RDI we're going to use for this. So currently we will get something completely random, which is not working properly, but it's not working at all actually. Okay, so we need to do an. We're going to give a uint adef, and then we're going to say it's going to be the C value type or something. I don't know, and I don't care. I actually do, but okay. So let's create a type definition. Type def enum. In this case, the enum will be uint ef blah blah blah, and this will be called the RTC value type. In this case, we have RVT. And we'll give it just the week, this RVT seconds, RVT minutes, RVT hours, RVT weekday, RVT day of month, RVT month, RVT year, RVT century, RVT status register A, RVT status register B. So in this case we can just say 0x0b for this one, 0x0a. This will let's see, century is 0x32, and now we have the year, which will be 0x09. Then we have the month, which will be 0x08, I guess. And yeah, 0x08. And then we have the day of month, 0x07. And then we have the day of month, weekday, 0x06. Hours will 0x04, 0x04, 0x03, I guess. Minutes. 0x02, okay. And the seconds will be 0x00, okay. So in this case we have to get weekday, which is get CMOS get value from the RTC. In this case, if we go to a test.cpp file, we'll probably get an error right now. we should have gotten an error. Now if we say get value, we go to std cmos rtc get value rtc value type, and we now want to have the hours. In this case, 15. Oh. In support instruction from MAV rtc s21. Okay. DL in this case, we're not moving a large amount, so we just use DL for this one. So and guess what? Now it's not working at all. 006, how about 76? Okay, so if EDI RDI, which is DIL, as the lower registers. In this case, you can say DIL. Should work now, or not. Wait. So we're currently waiting. Okay, so it's storing EAX right there, and I maybe have an ID why it's not working. So because we're waiting right here, request the data. Is it quite literally not capable of? What the frick? Okay, so we are currently requesting the weekday, right? Minutes. We are requesting the minutes, and the minutes are 0x02. Which is quite strange that it's not working, to be honest. 0x06. It's trying to read from it, but with RDI, EDI, DI, and DL, but DIL is what we're currently using, I guess. But why isn't it? So if you and HTF value type, and HT. So where is it going wrong? It's clearly going wrong right there. I'm not sure why. Ah. It has to do with the parameters. Doesn't wait, what? What the frick is this? We have RDI. It's currently DIL, where we're storing the value inside. Okay, we're storing EAX right there. We're moving something into there. We're requesting the data. We're returning it into AX. In this case, AX, EAX, AX, 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 AX. AX is the 16-bit register of RAX. RAX in this case is going to be cleared finally. The bit test. I really don't know why it isn't working currently. FAL and AX. I mean, it can't have to do with this or something. 0x07. This is the crazy part. So, one or another way. It's not returning anything anymore due to the value type we're passing in. As we do it now, it also doesn't work anymore. How crazy is that? Oh yeah, it was. It was working, wasn't it? Oh. Was this me being a moron? Okay, well. That's working, so I want to actually put in this one again. It's not. It doesn't have to do with the calling convention, that's for sure. But if we go in here and I want to move DLL onto AL, why are we actually moving it to AL if we just do this directly? So I want to write DLL to this one. Okay, operand mismatch. So in this case out, in this case DLL. Out wants DI maybe then. Okay, it needs to be in AL. I really cannot figure it out. DI, wait, what? DIL cannot be made when using. Okay, so it cannot compile some other way, which would mean that we are fucked. We are fucked. I don't know why we can't do this. So we need to compile with fpi is what it's saying, right? I don't know why, but let's do it. Okay, so we cannot use it. Ah, crap. Okay, can we use DL then? RDI is first one, I'm pretty sure. EDI. What is this? Come on. Wait, what? DI can't. RSI still. Okay, so some or another way. We are not allowed to use RDI while that clearly is the first one. Okay, 0x07. How about it? Now it works, right? Yeah, it's working. Yeah, of course it's working. Okay, so you're probably asking, well, look, What does this mean? Does it mean that we're completely screwed? Well, nope. There are still a few tricks in the house that I'm going to try out. And if this EDI cannot be used when making a pi object, what? What is this for a... Oh. Is it just me being stupid again? I guess it's just me being stupid again. It's working. Yay! Okay, so in this case you don't need to do this because we're probably the inside of it. Okay, so now in our test.cp file we're having minutes. In this case, I don't know why, it's 15. Let's actually check the RTC time. Current RTC time. I don't know why it says 51. Goes at 15 hours, right? 19 hours? What? Okay, so it's counting, but it's not counting properly. That's but at least we know we can access the day of the month. I mean, this one is correct. It's the, isn't it? Is it? It's correct. It's the 4th day of the month. RVT seconds doesn't work properly though. This one is 8, 9. Then it's going to be 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 22, 26. I do not know what the matter with this. It doesn't make any sense to me, the seconds at the moment. It's, yeah, it works, but then it doesn't work. So let's actually see what they have to say about the format of the... Okay, okay, formats. There are 4 formats possible for the binary or BCD mode, for hours, 24 formats. The format is controlled by static variable B and some of the RTC. The format cannot be changed, so your code needs to be able to handle all 4 possibilities, and it should not try to modify status register B settings. You always need to read status register B first to find out what your format will arrive in. Binary mode is exactly what you would expect the value to be. In BCB mode, each label has been modified this by decimal number. Need to expect. Okay, so well, let's actually get our full date. I want to create a date object, which in this case contains our, which will be a struct. So if we go to our CMOS right here, we're going to say type def struct. In this case, struct will be named RTC time stamp. In this case, it will have a uint 8t adef, and it will be t seconds. U by default will be null. Actually, no default at all. Uint 8 f t minutes. Uint 8 f t hours. Uint 8 f t weekday. Uint 8 f t day of month. Uint 8 f t year. Uint 8 f t century. I'm actually kind of curious what the year is according to the CMOS in my computer. Let's go to our test file. Here, let's actually check our year. Is it 2020 according to this, or are we living somewhere in the future? Actually in there. 5th month, right? Yeah. It does. The date itself is fine. You just need to turn it into the correct state. Yes, that's not fine. Uint 8 ft century should be it actually. So we're going to say void get timestamp. So in this case, when we are getting timestamp, we want to have a RTC timestamp pointer to t, which will be the return value for us. So in this case, if we are going to do this, so we're going to create a CPP file, which will be pretty nifty. I don't know what's the word for it. It will contain, in this case, this piece, and this piece will in this case just, in this case, going to be setting the value. So in this case, I'm saying in this case a lot. What's the issue, motherfucker? Incomplete type is not allowed. What? Are you kidding me? Oh yeah, of course. We need to say include CMOS actie t century, as in this case get value f CMOS get value f CMOS get value get value. I'm going to say RTC time value type, in this case century. We're going to have we have the year, we have the weekday, we have the seconds, the minutes, we have the hours, and we have the day of month. So currently, if you create a struct like that into a test.cpp file, so right here we're going to say std CMOS RTC t give me a second, I'm gonna grab something to drink. Okay, well, so now what we need to do is create a string concatenation function so we can start creating our string. But currently, let's see if it actually works. Ooh. Multiple definition, you know what it means? I don't. Well, so apparently It does not understand. Okay, well. These things are the things I hate most in life. When I need to spend my time on fixing stuff like make files, like let's see if it works without him. It doesn't. Multiple definitions. Yeah. And why is this happening? I'm pretty sure if we do this it will just work fine, but then we'll get the error because there's no there. Fuck. Okay, so we have the auto get value and I don't care if we do this. Come on, G++, why are you so bad? You're the worst compiler ever. Really, man, this really sucks.
So apparently it doesn't understand.
If we want to join them. And then eventually the linker is going to be like, well, frick you. Which he is completely wired in though, because after that we're going to create our Visa BIOS small library, which will enable us to print text on most displays of modern computers. Later on, maybe when we want to support all the computers, which we probably won't because we're creating a 64-bit system, we will use the VGA buffer, VGA text mode. Let's actually see my YouTube video. My condolences for everyone who had to listen to that. Okay, either way, we're going to create a string concatenation function so we can concatenate strings. Well, I just realized that something that I just did is causing multiple definitions. How stupid is that? So, well, since we can't use inline functions, we have to actually deal with this in like this. I don't like it, but we have to do it like that. So let's create our concatenation functions. Concatenation functions are actually pretty easy in C++, and that's why I'm going to create them with you guys. Eventually you have to be able to do it on your own, but let's first of all, let's do it together. Alright, let's do it together. So here we're going to say fstr concat bytes, and this will concat them. So we're going to say char pointer target A constant char pointer B. You're probably asking, well, why is it constant char pointer B? Well, because constant char pointer B will be constant. We won't modify the second memory address. I'm just interested in incrementing the memory address itself later on. Okay, so since everything we're currently doing is working fine, we're going to create this right here. So we're going to do global, and let's actually see. Okay, so all of this is nicely commented. So we're going to say converts int to a string. I know this code looks hard, but it's not hard at all. It's actually quite simple. If you're a complete crazy motherfucker. And I'm crazy. I can assure you that I'm fucking crazy. Okay, first of all, what we're going to do, we're going to find the end index of the word string. So we're going to say finds the end index of the first string. Or by the way, what we're going to do later on is this case Visa BIOS extension. I've never worked with it, but it basically allows us to this will allow us to okay, whatever. We're going to use this in this case. We can see the way how we stored the words. Mode what? Mode numbers. Okay, so we can actually use a lot of colors, and as you can see, we can use high resolution. In this case, 1280 times 1024, which basically is the largest size that the Grub bootloader supports, so we can quite literally work in the way that Grub bootloader works. So other commonly available graphics modes. In this case we have a lot of them, and I don't have a single idea on how I am able to get this working, but I don't give a shit, we're just going to try it. As you can see, we can even support 1920 but with 256 colors. It's a ton of colors. Oh wait, Linux video mode numbers. We're not using Linux. We're limited. We're really limited. Okay, however, so we're going to find the first index. In this case, like I said before, we need to find the null termination char. So in order to find the null termination char, we're going to find 0, and we're going to find 0 by putting it in the AL. So we're going to say sets the search bytes. It's a byte, it's an octet. Great word. Okay, and what we then want to do is we're going to webnis casb. In this case, webnis casb. Webnis casb. If I'm not sure, but let's actually see. We have console chop and D. In this case, EDI is casb. Yeah, it's working fine. It's going to read from EDI. So now we're going to say finds the final, finds the increments RDI until null term char. Oh, look at that! This is so sexy. It's just there. It's okay. So it finds the first char. Currently, we already found the first char, which is really cool. We actually all of this code right here. It's a lot of code. Of course not. What we did right here is just say we want to find the null termination char of the first string, which is stored in register RDI, or not actually in register RDI. It's stored in the pointer. The pointer is stored in register RDI, and the pointer contains the value to the first memory address of the string. So in order to now concat the second string, we're going to say starts the concatenation. Ooh, I actually made a freaking mistake right here. We cannot do comments like this. We're living in a good language. It's the Python command style. Python, yes, the worst language ever. Okay, so we're going to say starts the concatenation. I don't know how to spell that, but I don't give a frick. Okay, so we're going to create our loop right now. So we're going to say loop. And first of all, in the loop, we're going to have actually completed nothing. We're going to use scasb, so scan string bytes, scasb and stosb. In this case, scasb will scan. We're using scasb. Yeah, scasb will read from RSI. Now we'll read from RDI, and stosb will write to RDI. Let's Google these up. Stosb. Let's see what stosb is doing. Oh yeah, lotsb is what we're lotsb. Lotsb, not scasb. Store AL, so stosb in this case stores AL. And now if you do lotsb, lot string byte. This is so freaking easy. Okay, so here we're going to say loads char from memory address and incs from ESI and increments. Now we're going to say stores the byte. Stores AL into EDI. Cool. Okay, so now we want to check performs the operation. Performs the operation. Checks if we need to continue. So basically, by checking if we need to continue, we're going to use test. We're going to compare, in this case 0 against AL. AL in this case contains the current byte. With the current byte I mean A, B, C, D, E, F, G, H, J, K, L, M, P, Q, R, S, T, U, V, W, X, Y, Z, and of course \0, 1, 2, 3, whatever. So here we're going to say compares 0 against current char. Okay, so that's amazing. Now we can just say G and Z. So jump if not 0. So if it's not equal, we want to jump again to this loop. So okay, so jump if not null term. And I can say it might look ridiculous, but this is it. This is everything you need to concatenate two strings. You're probably like, look, that's impossible. That's completely impossible. Well, I can tell you it's not. Now if you go to our types test.cpp file, we're going to create a simple buffer. Let's actually comment this out because we're going to reuse it later on. So we do need this full system access though. But we're going to create a buffer char buffer. We're going to create a buffer of 64 characters, which will in this case contain hello fucking no, I cannot do that. Hello world. And then we're going to add a comma, and then we're going to say char buffer. In this case, this buffer will be automatic sized because we don't need to concatenate anything. Hello world, look. And we're going to add a smiley right there. Okay, so now if we do str concat bytes, and then we're going to give buffer 0 and buffer 1. We're either going to get a segmentation fault or we're going to get a functioning function. Well, what's the issue? Buffer, oh yeah, buffer cheese or something. Cheese buffer. Visual Studio Code, you had to be. Oh wow, maybe it just works, right? How crazy would it be if I was white and it worked? Almost impossible, isn't it? But check out this. Oh, didn't work. Or did it? Nope. Okay, well, that's depressing. Repeat not equals scan string bytes. Did it find the null termination char? I think it did. Load string byte. AL. Yeah, I need to drink water right now. We have stas B. Yes, I know what the issue is. So in this case we found the null termination char included, but we want to exclude it, so it will be overridden. And currently we concatenate the string successfully, but we did not concatenate completely because we found. Let's just show you. Okay, so if we now do dec, in this case I'm going to say AL. We want to decrease RDI or EDI actually. So we have RDI. I want to decrease RDI because it's a pointer. Now if you do this, take a look at that. It's concatenated, and you're probably wondering, well, look, why is it concatenated? Well, currently if we do. We add a comment and we're going to say allows override of the first null term. So because we found a null termination char, we will append after null termination char, while the std south function and other CPC functions actually stop at the null termination chars. In this case we want to override the null termination char, and we can do that by decreasing the pointer, so it will be written right there. It will start writing right there. So as you can see, we have our beautiful concatenation function ready to be used. Yeah, it's working. Okay, so this is all the assembler code we currently have until now. It's performance, it's ugly, it's actually kind of beautiful. I'm kind of in love with it, I think. But it's beautiful, it's really beautiful. What we now want to do is actually get our date string to function, because I mean, what is a RTC clock in your computer? What does it mean when you can't see it as a human? I mean, it's a lot of work, it's really cool, but we are humans and humans want to see the time as a string. if most people don't even know what a string is, but okay, so I'm going to say void generate RTC string. In this case, we'll run to RTC timestamp pointer t, and we're going to make it a constant because why not? And then we're also going to have a char pointer, which will point to the return value, the return address. In this case, the return address will be a buffer of about 64 characters. That's recommended. On the stack, of course, the heap is completely no-go for us at the moment. Yeah, that's kind of sad. I need to program my own heap manager. This is going to suck. Okay, so the wet. The wet. In this case, what we want to do with wet, we're going to set the first null termination byte. So the value. So we're going to say the value of memory address ret at 0. What am I doing? We can just say ret 0, right? Yeah, back to 0. Yeah. Okay, so currently we set the null termination char. Now we're going to say str stack f str. We need to include strings. This is going to cause issues, I'm pretty sure. Include. This is going to be a really hard laugh and cry at the same time. It's not working. Oh, it's working. That's great. F str cat bytes. In this case, we're going to give the memory address to ret 0, and then we're going to say which one? Append. In this case, we're wanting to append hello. Hello, mother. Okay, and now we're going to say std south. We're going to create a buffer, so char buffer, which will be 128 for now. And then we're going to say std cmos rtc is this get rtc string. And now we're going to give the memory address to t, and then we're going to say buffer, and then we're going to say std south buffer std endline, just like that. Now if we run this, we will get hello motherfucker. Oh my god, it's kind of crazy. I haven't had sugar at all, but it's most likely because I'm inside all day. Okay, so Google RTC date format. Year, month, day, hour, minutes, seconds. Okay, we're going to do that, I guess. So first of all, we're going to append a string right there, or actually not. So we need another buffer. We're going to create a buffer numtemp, which we're going to call it. In this case, the maximum number we can store inside of one of those is 255. So in this case, we're going to have 255, 3, 4 buffer. So we're going to get char buffer, which will be 4 in total, because we can't go behind 3. We can't go further than 3 digits, but we can also. We need to add a null termination char. So I'm actually kind of curious if we have any memory leaks right here. I'm pretty sure there are memory leaks, but it's currently not the thing I'm going to be focusing on. So actually see if blah. It's adding to null termination char, I hope. CMP. Oh, that's kind of okay. It's doing it properly. Let's actually add a little bit of space right there. Great. So take a look at this. This is great assembler code I've been working on for way too much time. But now we're going to do fstr un32. Oh no, did I just... Is it... No! Is it possible to perform a cast in this? So we have tt... Oh no. We can't, right? We can? Okay. We just need to make it a uint32f. That's crazy that this is working. Also need to add a concatenation function for those things, but I don't care. So, okay, that's not what we want. We want to add 0, so we're going to have integrate 0. Oh my god! Oh my god. This is okay, wait. Let's actually see where the RTC date has been started. So RTC start date. $1970, okay. $1980, I guess. Then when oh wait. Ah. Okay. 1990. Oh wow. Okay. 2022, and this doesn't make any sense either. 1988, 1988, 2020. CMOS start date. Is it possible 1998? Actually grab that example, I'm not sure. Current year. Yes, but what is current year? You have to modify the current year. That's stupid. That's really stupid. Okay, so that's not going to be functioning. Okay, so the year already sucks, as far as I see. Okay, well, I mean, it's not the worst thing or something. Okay, so well, now we need to get our so we have the month. That can be right. Did you forget a month? Huh. I'm a complete idiot and a month is in there. It needs to be converted in local time, that's for sure. Okay, I'll be right back. currently having my manual right here from GNU Grub. It's the bootloader we're going to be using, so I'm going to open my manual and we're going to check out how we can create a bootable ISO. Okay, so I already know it slightly, but I want to currently do it without any examples, just by own experience. So one thing I'm already going to create is a so-called ISO dir. Can I just say disk ISO disk image and then boot raw ISO dir. Okay, so I'm going to have a folder called boot and then grub. So actually I need to check this how I did this before. We have ISO dir, we have boot, grub and grub.cfg. Alright. So, one thing that's really important, that we also create a boot.asm file. So, boot.s, which will be later on used, currently not. Currently I just want to check if I can even make a bootable system with QEMU, I don't know. Okay, so we're currently able to build, so we are currently having test, but we also want to have the default build and run. So for that one, we are going to first of all write a config file for grub. So I'm going to grab my manual. If people want to read with me, I can obviously turn on my camera. Let's do that. I'm not going to show my face, of course. It would be not required for this. Let's actually check out. Alright, so we're going to add a new video source, video capture. The question is if it will work. Well, it is working. So as you can see, we have the grub manual right here. I know it's a bit satanic, as you can see, but I mean, those guys made 90% of the whole internet, basically, eventually. When you look at what they did, they didn't build it, but they did build the foundation for it. So this manual contains everything about GNU Grub and how you can do stuff with it. I mean, well, let's start reading it. I'm not sure if it's even good visible from here, but yeah, whatever. So, it's from Gordon Metzke, Yoshinori K. Okuji, Colin Watson, Colin D. Bennett. Okay. So first of all, we're going to check how we can write our config file, which is actually really important. I don't want to use DOS, I don't want to use Windows. I really hate Windows. I think there's guys who made this too, otherwise they wouldn't have made Unix and that kind of stuff, or GNU operating systems. So I'm looking how we can create simple bootable stuff. Okay, I know what the world of a bootloader is, I just want to see how I can fix these things. BIOS installation, boot grub. Okay, in this case when we want to create a okay, so let's grab some kind of clip so I can keep my, it's just my phone there. Lights up. Nothing interesting except other people, but I don't care about other people. Okay, so in this case I can see grub mk rescue, so I'm going to check how that works. So I'm going to cd into the ISO dir. That's actually grub Okay, so we made an ISO. Well, let's do QEMU, and then X system x8664, and then we're going to do test.iso. Well, we have grub. That's something. Let's say, wait. Okay, so that's something. We have ISO boot grub. We actually need to cd out of this. So we're going to remove the test.iso. We're going to create. Okay, so we can create ISO files. Let's store this to the build one. So I'm going to say grub mk resq mk resq /iso dir, and then we want to do O of os.iso. So when cleaning, we of course want to also remove the os.iso rm rf os.iso. Okay. So when we currently, let's just try this out. So right now we're doing make build. It will create an ISO file. So that's really cool actually. So let's say creating ISO, building disk image. Okay, building disk image.
Cool, that's really cool.
Okay, so now I'm seeing right here we have mk rescue, which basically does nothing that's important. It will just create an ISO file for us. Well, in this case, grub.cfg will contain our configuration. See menu entry. We can create menu entries. I see part of it. I don't care actually about that. So if we want to add our operating system, we can add a menu entry. So let's check it out. So menu entry. Let's say simple C++ kernel. Advanced. Actually, if we want to add a hard, we can do \7, I guess, and then we can say nothing yet. Let's see what we actually can do. We need. I don't want to. We're not doing anything special, so I don't want to set our roots. Okay, so we also need to configure how the input is going to be supported. We're going to support the console and serial, so we're going to say grub terminal input, going to accept console serial. Okay, okay, so we can boot default one if we like. So we can say grub default, and by doing that we can just give this as our default bootable. Now we can say grub timeout, have seen. So here we have grub timeout somewhere. Grub timeout should be equal to, in this case, Default value is 10. We're going to set it to 10. So I'm actually kind of curious if we do this. So we're currently writing our... Oh, I don't want to write the test ISO, I just want to build it, okay? It's going to make build. Alright, but what if we... let's do make run. Is in this case going to require build. And then we're just going to do QEMU system. See how we can emulate such a system somewhere right here, yes. We're creating images, but I just want to see how I did emulation. So QEMU system x86 64-bit, and I'm going to use os.iso as input file. So what about build run or make run? Okay, well, it's something, but it's not showing our menu. Let's actually see what else I did. I did something before right here in BOS kernel. Okay, let's maybe that's the issue. / boot. Not sure yet. Boot os.bin. I'm not sure. It will most likely not run properly. Oh yeah, there we go. Well, I mean, it's there. Let's do this. Actually, I don't know. The grub timeout is not set. I guess maybe we need to make the string then. What if I set it to 0? Let's see if this actually does anything. Okay, some other way does not do it. We need to set the grub default, but we have a menu entry. That's not to do a default one then. Okay, so grub distributor. Book. Sure what this will do. Grub distri. This one clearly doesn't work. you hear anything? Grub init tune. Sound HV all. Okay, the audio is not working. I don't. Let's give some let's give 2 cores. SMP, let's give 2 cores. M1024. Okay, that's yeah, that's not going to work. QAML fees. Yeah, okay, I guess Visa is supported by default. Now another thing that sucks that we need to create menu entry search as we would label grub. We can style a grub, but I don't know why or how. The grub graphical management support teams there. Customize the layout and appearance of grub boot menu. The theme is configured to a plain text file that specifies the layout via GUI components, including the boot menu, timeout, explorers bar. But where? How can you activate such a theme, please? I'm interested. It's most likely not going to be specified, but I really want to know. Yeah, idiots. You know what? We have a boot menu. I'm going, whatever. Good enough for me. I'm not going to customize it because I tried it last time. It was busy for hours and didn't work because it's just really bad documentation on anything out there. Or maybe the VM doesn't support it. I don't know, but I'm not going to try either because it's going to take way too much time to actually figure out how to fix such a thing. I mean, we have a boot menu. We can, yeah, this works. It works. That's all I currently need. Now we need to also create an assembly file, which will, yeah, we already have it, boot.s. Okay, so when making, we want to also assembler, so as.m 64-bit assembly file, if possible, of course. Boot s so. I'm going to put on some music for myself because we're going to figure out a lot of things which are not going to work. I'm not going to use an already existing one. This I'm going to do is completely on myself. I'm going to create my own bootable assembly file because I'm not an idiot. Then we can start using Visa mode, but first of all we need to at all get something functioning. Cool. So boot as is working, we also need to create a linker config. I'm just going to use the linker script that was already supplied. I want to know how to do this. I don't accept writing code over.
And then in the relocation information section, it says, okay, well, any instruction that is depending on something else, we're going to specify what it's depending on. So, for example, in this first entry in the relocation information section, the load word instruction is depending on X. Okay? And we can note up here that X is going to be part of the data set. Okay? So X is referring to a location in memory where we're going to go and get some data from. Okay? That's what the load word instruction is going to do. The JAL instruction is depending on procedure B. Now, here's the thing. Procedure B is defined in a second header file. Right? So I've got two different header files here. One and I have two. So in object file number one, I'm going to be making a jump to a procedure that's defined in object file number two. Okay, so those memory addresses got to be resolved. And I got two different object files pointing to places in the other object file. And so I have to specify where that's at, right? So the linker needs to go through and fill in the details in terms of where is everything, right? Where is everything? And that question is going to be answered in terms of memory addresses, okay? So these two object files have to be combined into a single executable, right? So that's where we're going with this, right? So once that's finished, we have a program that we can actually execute and run. Okay, so object file and executable file, very similar. It's just that the object file has all of the memory addresses figured out. And inside of the executable file, you know where everything's going to go. The location of everything is specified. You're good. Okay, now in this example, you can see the text segment and data segment. We actually have the names of the instructions. That's just for the purposes of the example. If these were real object files, it would just be zeros or ones, pure machine language. But this information is encoded into the object files. So let's just go ahead and start doing what the linker would do. Okay, so in the executable file, it needs to know what the final text size is going to be. Right? The text segment of the program, how big is it going to be? Well, how can I know? If I'm combining these two object files together, I can go look in the header information I said before. In object file 1, 100x. Object file 2, 200x. Right? So the final text size, or the final text segment size, the executable, is going to be 300x. Now what about the data segment? Well, look in the object file 1, it's 20x long. Look at object file 2, 30x long. So we're going to have 50x. Okay. So now, what about the instructions? Okay, so the instructions that we need to have memory addresses reserved. Where are we going to start? Where's the instructions going to start? Where are they located? Where we jump into? Where we loading information from? Okay, well, let's look inside of the first object file. So there is a load word instruction, okay, and that's going to be the first instruction in our final executable file. Okay, so where's that going to be memory? Well, in this program's instructions start. Okay, the instructions that you write, they start at 400,000x. So guess where the memory address, guess what the memory address is going to be in this first instruction, this load instruction.
Oh, that was moving.
That's right. Okay. So the jump instruction, which follows immediately afterwards, where's that going to be? Well, it's one word later. Because remember, all instructions are one word. So its memory address is 400,000. X, right? Now dot includes all the rest of the instructions that would make up the text size. We're only concerned for this example, and later we're going to be concerned with filling in the addresses for the individual instructions and also for all of the relative instructions that we're counting. Okay, so all the rest of these, the dots, this is the remaining instructions for the example we went over. Okay, they would be having their memory addresses filled in just like we did for these first two. Okay.
Twee dislikes. Ah, sukkels. Okay.
So, what about the location, the data segment for the beginning of the data that's being referred to as X and being referred to as Y in the separate object files? Okay, so those guys are going to be assigned to the starting point of the data segment. So X is going to go at the very, very, very first memory address of the data segment. MIPS, that is at 1 million X. So if X is going to be the beginning of our first chunk of memory in the data segment, what's the memory address? X. So what about the Y? Okay. Well, how big is the data segment in object file 1? 20x. So the Y follows immediately after the x. So guess where that's going to be? Which reminds me, what about the instructions, the beginning of the instructions from object file 2? Well, how big was the text segment in object file 1? 100. So, where do you think this is going to start from? Here, this is where the
Man, je vraagt toch nog, ik vraag om linkervals.
And this article is expressly for people who know next to nothing about command files. If it's the only other material. So, how do you go about finding more details about the command files? Well, as a lot of habits, there is a wiki article dedicated to every topic. So, we're going to go to this is the homepage for the TI wiki about various processors we sell. Here in the search box, and primer. So, voila, the article comes up. Here's the full URL for it. That's what you want to focus on. And this article is expressly for people who know next to nothing about the command files. It's the only material. Gets into even lots of fairly detailed situations that tend to occur in actual live command files in the field. So that wraps it up. I'm George Mott for Texas Instruments. Thank you for joining me on this video.
In this short video, let's understand the Boolean sequence of ARM Cortex and processors. system reset sets all registers to their reset values, except for the reset flags in the client controller register, CSR, and the registers in the backend domain. A system reset can be generated by hardware or software. For example, if the RST pin is pulled low, a system reset takes place, and RST pin is pulled up internally within the processor chip. If the reset button is pressed down and RST pin is pulled low, when the reset button is released and the RST pin becomes high again, a pull-down capacitor is added and paired along with the reset button. This button
In the meantime, I'm going to create a CPU stuffing.
So because of backward compatibility, a lot of things that we have to do while leading operating system would reflect on what was done 30 years back. To think what happened in and a system to be around 95 that is the 386 these processors were used are still done today on the latest i7 processor. So we will look at how this is used. Now we all know that in order to start the computer, we need to press the reset button or the start button presently on the start. So what actually happens internally is that when we press this button, it is going to send a signal to CPU. The signal, for instance, would be a pulse, is an electrical pulse, which gets created when you press the start button or the reset button. And this pulse is sent to a specific pin on the CPU known as the reset button. And when the CPU obtains or gets this particular signal about the reset, it is going to start the boot time. So let us see what are the various steps involved when the CPU starts the boot. So we have seen the power on reset. Now when the power on reset comes and the CPU detects it, what happens is that every CPU register which is present inside the CPU is initialized to 0 except for 2 registers. And these registers are your code segment and the icon. Now when the reset occurs, the code segment is set to the value of 0xF000. The instruction pointer is set to 0xFFF0. So if you recollect how an 1888 or 1886 processor computes its address, it's going to take the code segment register, in this case F followed by 3 zeros, shift it by 4 bits and add the instruction. As a result, physical address or the address for the first instruction to be executed will be present in FFFF0. Now if you look up the RAM module, which we have covered in the previous videos, what we could see is that the memory address corresponding to F0 would be pertaining to the BIOS area. In fact, this particular memory location is just 16 bytes below the 128. So this particular thing 0x 1, 2, 3, 4, 5, that is 1 is this particular point or this particular address, and the first physical address that is put on the address bus by the CPU is FF0, which is 16 bytes below this particular memory. So as a result, if you want to boot your system, it should be ensured that at this particular memory location we have the valid instruction which is present. This on waiting is the first instruction that is present. Now, another thing what happens is that as soon as the power is reset, the processor is set to what is known as the real mode. So in the real mode, the processor is in a backward compatibility mode with the 8088 So we collect that the 8088 and the 8086 processor could address at most this part of this part. This is shown as the green region in this part. There were other features of the real mode. We had no protection, no privilege levels, direct access.
Okay, you know what? I'm just going to read this documentation. Yeah, I have this code right here and I don't know what it means, that's the issue. Yeah, you know what, I'm just going to copy and paste it. I'm so sorry, brain. It's not satisfying to do it all. To copy code. Oh my god, I hate this. Okay, so we have our linker. Now we need to check how we can link files.